Now let's go for the circuits, the active circuits. The first one will be the inductorless wideband amplifiers. The first circuit we have designed, it's 2 stages shunt series feedback amplifier. The first stage is a simple common emitter stage, and the second one uses a Darlington for a higher gain. In the feedback network, we have a capacitor that reduces the gain at low frequencies, widening the bandwidth of the circuit. As you can see in the layout, the active circuit is about 0.3 to 0.4 square microns. The comparison between the measured and the simulation results for the gain, we have a similar curve, but about less 2 dBs gain in the measurements than in the simulations, showing that probably the active devices models are not also accurate. But we have obtained a very good bandwidth of 20 GHz from 11 to 31 GHz with a maximum gain of 10 dBs. Here are S parameters, and again we have differences between the measured and simulations, and in input we have worse results measured than the simulations, but at output we have better one. But anyway, they are on the range of minus 10 dB. So in next slide we have some comparison between similar wideband amplifiers, all with shunt series feedback amplifiers, and we notice that our work has a better gain bandwidth per unit area and slightly worse gain bandwidth per power consumption than a gallium arsenide technology that is much higher costly technology. Let's go for the even simple stage, just only 2 common emitter stages. We just put it this circuit because it's very simple. We have 2 transistors, no matching at all, just only the bias to test the accuracy of the active devices models. With this circuit we have exactly the same problem, less 2 dBs in the gain when we compare the measurements with the simulations. The shape is about the same, so we think that really the model are not very accurate. For the S parameters, we have in both input and output better results measured than the simulation predict. So let's go now to use the spiral inductors in the last prototype that I will present today. And this is a Cascode LNA. This is a classical low noise amplifier with an inductor. The input matching network, we have a compromise between noise and gain and matching. We have tried to use the inductor on the emitter, but instead of having an input, but the results were quite similar, so we have decided to have it at input for not reducing further the gain, because the gain is very low since we are pushing the technology to higher frequencies that the technology was optimized for. The output matching network, it's we are using the inductor, the collector inductor, that is the chuck inductor. That is not really a chuck inductor in this case, is also part of the output matching network, and we have a capacitor divider. The DC bias is like in the previous circuit, only made by a shunt feedback resistor between collector and base. The input and output coupling are made with 2 picofarad MIM capacitors. So here we have the layout, and for measuring this circuit we have not obtained exactly the same current, even pushing the bias voltage for higher values. We have only obtained on measurement, as I show in the next slide, results for a current of 1.8 milliamps. We could not achieve the 2.4 that we have obtained in simulation. So once again we have different values. Probably the transistors have lower current than expected. So in low frequencies we have good matching between the measured curves and simulations, but not for higher frequencies. But we have obtained 10 dBs gain at 25.6 gigahertz, because we have a shift on the maximum gain frequency, and we have probably the output inductor is higher than the value from the model. That's why we have this shift in frequency. So we need to have better models. In this circuit we have used the foundry model. Finally, for the input and output matching, we have very similar shapes on this circuit, but again the same frequency shift and the previous slide for the gain. For the noise figure, we have simulated 5.4 dBs gain at 28.5, but since the circuit was shift for lower frequency, we have measured at 26 gigahertz, where we have now more or less the same results as in 28.5 for the gain. We have 6.4 dB, so 1 dB worse than the simulations predict. So let's go to the conclusions of these results. The Pad and Thru models were obtained and used on measures calibration, but the inductance and capacitors of the lines and the pads are of the same order of magnitude as the components. So the errors that we have on this calibration are not small at all. So we have to take seriously the models of these unavoidable components of the circuit. The spiral models, we have obtained a new model that is accurate up to the millimeter wave bands, introducing these LR parallel lumped elements in series with the foundry model to include the skin effect, and the spiral inductors with higher series resonance frequency were designed and fabricated, and the models were obtained, and they are very accurate up to 45 gigahertz. So a wideband inductorless amplifier was designed, fabricated and tested, and it has a very good gain bandwidth per area and gain bandwidth per power consumption results, and an LNA with a noise figure of 6.4 dBs at 26 gigahertz and a gain of 10 dBs was also obtained. However, all these amplifiers has less gain than predicted by the models. So we need to have not only better passive components, but also look out to the active devices models. So thank you very much for your attention.